Okay, so today's talk is about how to assign probabilities and degrees of belief to indicative conditionals. And what we're going to do is start by briefly reviewing some of the problems that you face when you try to assign probabilities to conditionals, and then we're going to present a new theory of how to do that. This is co-authored work with Paolo Santorio, who's actually in the chat somewhere. He's in one of these cubbies. And the other thing we should say from the get-going is that the material we're going to present is extremely influenced by some research by Stefan Kaufmann that originally comes from von Frossen on something called Stalnaker-Bernoulli models, which we're not going to get into too much during the talk, but that's the main influence for the ideas today. Okay, so the talk I'm going to go through is going to really focus on this handout that I sent around. So if you don't have the handout, I think it will not make sense. So please make sure you have a copy of the handout, and let's begin. So what we're interested in doing in assigning probability to conditionals in particular is to validate a particular thesis about how you assign probability conditionals, which is sometimes called Stallneckers Thesis or Adams' thesis or sometimes Ramsey's thesis, and it's one on the handout. And in one, we use the term descriptive to mean any sentence that's not a conditional. So any simple sentence like it's raining or it's Monday, that's a descriptive sentence. And what Stallneckers' thesis says is that for any descriptive claims A and B, the probability of the conditional, if A then B, is equal to the conditional probability of B given A. So on the left-hand side, the arrow denotes the indicative conditional, not the material conditional. So the idea is the indicative conditional is something that's simply part of our conceptual life and does not have a pre-theoretic analysis. We're going to try to give it an analysis subject to satisfying this constraint. And on the right-hand side, we have the conditional probability of the consequent B given the antecedent A, which is either defined by or closely related to what's called the ratio formula. So that value is defined as the ratio of the probability of the conjunction A and B to the probability of A. Okay. So why would we accept Stallneckers' thesis? Well, I will give you an example. Imagine that Maria tosses or rolls or tosses a fair six-sided die, and think about what your degree of belief is in the conditional. If Maria tossed the die, it landed on 1 or 2. Well, the die has 6 sides. Each side is equally likely. So 2 of the 6 sides are 1 or 2. So that means 1/3 of all of the outcomes of where Maria tossed the die are outcomes where the die lands 1 or 2. And so we think that your credence in that conditional is 1/3, which is your conditional credence in the consequent, the die landing 1 or 2, given that she tossed the die. And basically we think many, many examples of this form satisfy Stallneckers' thesis. So we are interested in developing a theory of conditionals and probability that validates this equation. Unfortunately, though, there are these famous results called triviality results that show it's very difficult to develop a theory of conditionals and probability that satisfies Stallneckers' thesis. And we have a particular take on what's going on with these results. And in our opinion, what these results are about is the clash between 2 principles, between Stallneckers' thesis and another principle we call closure, which predictably we will say is the culprit to the problem. And what closure says is that the class of rational credence functions, so the class of probability functions that could model the rational beliefs of an agent, which we think are what's tied to our intuitions about the probability of conditionals like 2, that class of probability function is closed under conditionalization, which means that if a probability function is in the class of possible credence functions that a rational agent could have, then the result of conditionalizing that probability function on any other claim A is also in the set of rational credence functions. So PR dot A represents another probability function where the probability it assigns to B for any claim B is equal to the probability that PR assigns to B conditional on A. And I've noticed I'm already unhappy with how I've written the handout. Really the way I'd like to write it is Stallneckers' thesis should say that for any rational probability function, the probability of the conditional is equal to the probability of the consequent on the antecedent. So the idea is, well, Stallneckers' thesis and closure impose 2 constraints on the class of rational probability functions, and then we're going to see that that class of constraints is trivializing. And that's a proof from, I think originally David Lewis, showed that Stallneckers thesis and closure are together trivialized and they lead to an absurd consequence. And the absurd consequence they lead to is that any two claims are probabilistically independent. So the consequence they lead to is that for any claims A and B, the probability of B given A is equal to the probability of B. And I'll walk you through how that result works. And the result holds fixed kind of the basic classical rules of probability functions, the important one for our purposes being the law of total probability. And what the law of total probability says is that the probability of any claim can be thought of as the weighted sum of its conditional probability, conditional on various cells of a partition. So if you want to know how likely a claim is, just think of all the ways of dividing up logical space, find out how likely the claim would be given that you're in that part of logical space, and then weight it by your prior on that part of logical space. And in particular, we apply the law of total probability where we assess the probability of the conditional if A then B, and we assess it relative to the partition of logical space by whether the consequent is true. So we look at how likely is if A then B if the consequent is true, and how likely is it if it's false, and then we weight by that. And this is where the problem will come in. So the first step of the triviality result is that the probability of if A then B is equal to the probability of B times the probability of the conditional given B, plus the probability of not B times the probability of the conditional given not B. So that's the setup. And then what Lewis observed is that if you have closure and Stallneckers thesis, you can derive line B, which is going to create all the trouble. And line B says, okay, how likely is the conditional on B? How likely is if A then B conditional on B? And it's 1. That's the problem, is if you accept closure and Stallneckers thesis, it's 1. And ultimately, we're going to give a theory that rejects closure and so rejects this step of the proof. We're going to keep Stallneckers thesis but deny this step of the proof. Why does this step of the proof work? The problem is, by closure, we know that when you conditionalize on B, the posterior probability function still satisfies Stallneckers thesis, because the posterior probability function is a rational probability function, and rational probability functions satisfy Stallneckers thesis. And the problem is that the posterior probability function, when you take PR and conditionalize on B, it has its own conditional probabilities. And it assigns a conditional probability to B given A by the ratio formula. And the probability it assigns to B given A is 1. And so the problem is, if you look at instantiate Stallneckers thesis, where PR is the conditional probability function of the original PR conditional on B, and the right-hand side is 1, and so the left-hand side is 1. And for similar, the idea is once you conditionalize on B, conditional on anything else, B has a probability of 1, because you've zoomed into the B worlds. And similarly, once you've conditionalized on not B, B has a probability of 0 conditional on anything else because you've zoomed in to the not B worlds. And so applying Stallneckers thesis, the conditional if A then B has a probability of 1 given B and has a probability of 0 given not B. And so we can move to line C by instantiating the equations in B in our original equation in A, and we get that the probability of if A then B is equal to the probability of B times 1 plus the probability of not B times 0, which means that the probability of the conditional, if A then B, is equal to the probability of its consequent. And finally, we close the loop by applying Stallneckers thesis one last time and instantiating if A then B for a conditional probability. And we get that the probability of B given A is equal to the probability of B. A and B are arbitrary, and so the triviality result we've had is that any two claims are probabilistically independent, more or less. Roughly, that's how the result works. Okay. So that's why you can't accept both Stallneckers thesis and closure. We like Stallneckers thesis, so we reject closure. I should say, though, that one other way to wiggle out of this business is we have assumed that probability works using the usual axioms of the probability calculus, and that was in line A when we accepted the law of total probability. There are some treatments of Stallneckers thesis that keep closure in Stallneckers thesis but give up the law of total probability when you have conditional instances. But we're not going to do that. So we reject closure. We think that conditionalization is not the way that rational agents update their credences over time. That may be very upsetting, but the salve is that conditionalization is correct whenever you don't have conditional claims in the mix. It only delivers wrong predictions on our theory when you assess the posterior probability of a conditional. And we think that there's empirical basis for this claim. And to give you a feeling for why we want to reject closure. We just want to show you that we think that your credence in a conditional, when you learn a new claim, does not evolve by conditionalization. And here is our evidence. Return to the die case. And now compare the probabilities of two different claims. The first claim is that the die landed even. The second claim is that if the die did not land on 2 or 4, it landed on 6. Well, your prior that the die landed even is going to be 1/2. What's your prior in the conditional if the die didn't land on 2 or 4, it landed on 6? We want to compute that by Stallneckers thesis. So let's think through it. If the die did not land on 2 or 4, how many possibilities are left? 1, 3, 5, and 6. So there are 4 possibilities that remain if the die didn't land on 2 or 4, and only one of them is 6, and they're all equally likely. So that means the probability of this conditional, if it's computed by the conditional probability of landing on 6, given that it didn't land on 2 or 4, is 1/4. And this table summarizes the second row of the table, I guess, if there are 3 rows, summarizes those predictions that we think your prior in A and B is, well, your prior that the die landed even is 1/2, and your prior in the conditional is 1/4. But now think about if you learned that the die landed even. So you imagine becoming certain that the die landed even. What would your new credence be in the conditional if the die did not land on 2 or 4, it landed on 6? Well, let's think about it by applying Stallneckers thesis. If you're certain the die landed even, which you've just learned, you have 3 possibilities you've left open, that it landed 2, 4, or 6. When you conditionally suppose that it didn't land on 2 or 4, that leaves one option left, that it landed on 6. And so once you've become certain that the die landed even, the conditional probability of landing on 6, given that it didn't land on 2 or 4, is 1, and we think that appropriately reflects your credence in the conditional. And so we think, and this is what's summarized in the last row of the chart, that after you've learned that the die landed even, your posterior in the claim that if the die didn't land 2 or 4, it landed 6 is 1. And our point is, if you want to get those predictions, you have to reject closure under conditionalization. And the reason for that is the conditionalization has the following property in general. For any claims A and B, if your prior on A is less than your prior on B, then once you conditionalize on B, your posterior on A is less than 1. Why is that? Well, in picture thinking, semantically, if the probability of A is less than the probability of B, then there are some situations that you assign positive probability to where A holds and B, there are some situations you assign probability to where B holds and A does not, because A is less than B. When you conditionalize on B, those situations you're still assigning positive probability to. So you're assigning positive probability to some situations where A does not hold and B does, even after you've learned B, which means you have a credence of less than 1 that A holds. So the point is, if you want to vindicate the predictions in table 5C, you have to reject closure under conditionalization, and we like those predictions, so we reject closure. Okay, so that's our intro to what we want to do, and now we're going to develop our theory of conditionals and probability in 3 steps. First of all, we're going to give you a new semantics for conditionals in a framework that Paolo has developed called path semantics. Then we're going to give you a general framework for thinking about probability once you're using path semantics, and then we're going to give you our theory of updating. So intro to path semantics, which is a Paolo thing. In path semantics, the meaning of a sentence is not a set of worlds, it's a set of paths, which are richer than worlds and are built from worlds. A path is a sequence of possible worlds, but it's not just any sequence, and this is where we're departing from the von Frossen, Stefan Kaufmann way of doing things. A path is not just a sequence of worlds, not any old sequence, it's a sequence of worlds without replacement. So that means you can only put each world in the sequence once. And also, we're going to be interested in sets of paths that are all built from the same pot of worlds. So basically, you take each world in your pot and you put them in an order. So paths are linear orderings. And then we need some notation. Well, first of all, we do still need possible worlds. And what possible worlds do is they assign a truth value to every atomic sentence. And then we need several more definitions. The next thing we need is P sub I, when P is a path, is the ith member of sequence P. So if you have a path WVU, P sub 2 would be V. And then next what we need is we need a way of talking about sets of paths that begin with a certain sequence of worlds. And that we use single brackets for. So if you have single brackets WUV, that denotes the set of all paths that begin with the sequence WUV and then have some extra worlds added on. So that's some, sorry, there's an unpleasant amount of different notation here. And then the reason we're introducing paths is that the meaning of each sentence is going to be a set of paths, and that's assigned by this interpretation function denoted by double brackets. And then we need two operations on paths to state the, oh, actually, no, we don't need that. Sorry, that's for another part of the paper that is not presented today. Good, okay, we're gonna skip 3. Paolo, can you double check that we don't need 3 today, looking through the handout, and interrupt me if I'm wrong and I'll go back to it. So we're gonna skip 3, it's not needed for today. And, oh no, we do need it. Okay, sorry, we're doing 3. Okay, so then the 2 more things we need is paths or sequences. We need to define a notion of a subsequence, or a subpath. The subpath of a path can have less worlds, but they have to be in the same order. So if you have WUV and you remove, if you have the path 1, 2, 3 and you remove 2, and then you have 1, 3. 1, 3 is a subsequence of 1, 2, 3 is how we're thinking of it, is you just remove some worlds but keep the order. And then finally, we need permutations. And the permutation of a path takes all the same worlds, but puts them in a potentially different order. And the reason for that is we're going to be thinking about every permutation of a path. Okay. And then the last thing we need, and that's why we define this technology, is P plus A, which is when you update a path with A. And unsurprisingly, the semantics of conditionals will be understood in terms of updating a path with A. And the way we think about that, and this is our second departure from the sequences in the von Frassen and Stefan Kaufmann's work, is we're defining the update of a path as when you update a path with A, if it's like it's raining, you update a path with it's raining. You got all these worlds. In some of the worlds it's raining, in some of the worlds it's not raining. If you want to update your path with it's raining, you remove every single world where it's raining. And then just, so you remove them all, but keep the same order of the remaining rain worlds. Which means what you do is you find the largest subsequence of the path where A is true throughout the path. And A being true throughout the path means that it's true at every permutation of the path, is how we think of it. Doesn't really matter the details. The point is the metaphor of if you want to update a path with A, you remove every not A world. Okay? And now that we have paths under our belts, all we need is how we'll just interpret a simple propositional language with ordinary connectives and then an indicative conditional. And the way you assign sets of paths to these things is anything that's descriptive, so it doesn't contain a conditional. All it cares about is the first world in a path. And then conditionals are what actually use the structure of paths. And so the way we do that is say any atomic claim is true at a path, just in case it's true at the first world in a path. Negation and conjunction are Boolean, and then the conditional is what matters. And as you would expect, as always, the way it works is the conditional is true at a path, just in case if you update the path with the antecedent, the consequence is true there. And here's what the key thing in that is, though, is that a conditional is true at a path, like make it a conditional with just like it's raining, like just descriptive A and B. So A and B are just true at sets of worlds. Then in picture thinking, that if A then B is going to be true at a path, just in case you take the path, you remove all of the not A worlds, and then the first world in the path that's remaining is a B world. So the consequent only has to be true at the first world in the resulting path. Okay, so to illustrate all of that, I'm going to give you some examples of several sentences that are true at a path. So I'll give you, and there's going to be a couple different examples throughout the talk. Our first example is we got a path with 6 worlds. And the 6 worlds you can think of as modeling the outcome of a fair, die roll. So world 1 is where the die roll is 1. So we got the path 1, 2, 3, 4, 5, 6. And at this path, it's true that the die landed on 1, because that's true at the first world in the path. It's also true that the die landed odd, because that's true at the first world in the path. It's also true that if the die didn't land on 1, it landed on 2. And the reason for that is, well, what you do is you update the path with it didn't land on 1. And to do that, you remove world 1. And the resulting path has world 2 as the first world. And at that world, it landed on 2. And so the conditional is true at the original path. I'll give you a second example of a conditional, now an iterated conditional. Iterated conditional is in the form if the die landed odd, then if it didn't land on 1, it landed on 3. And to compute this, first we update our path with the claim that the die landed odd. And that gives us in 6E, the following path, W1, W3, W5, because what we do is we remove the worlds where the die didn't land on, but preserve the order of the remaining worlds. And so that gives us a 3-world path. Notice it's important that the number of paths in the posterior after updating is different. It's less than the number of paths originally, which is kind of, it makes you think, because suddenly, oh, we're looking, you could start with a set of paths that all have 8 worlds, and then once you update those paths, now they're all going to have 7 worlds. So that's important later. Okay. So now we have this updated path, P plus odd, and to compute the conditional in 6F, what you do is you compute the consequent, which is itself a conditional. If it didn't land on 1, it landed on 3, relative to the updated path 1, 3, 5. If you want to compute the consequent at 1, 3, 5, you update 1, 3, 5 with not 1, which gives you 3, 5. And then since 3 is the first world in that, it landed on 3. And so you can see how the computation of iterated conditionals proceeds. And the other thing you can notice here is that when you assess that consequent conditional, if it didn't land on 1, it landed on 3, the whole path you look at is completely made up of worlds where it landed odd. And so that conditional supposition that it landed odd is retained throughout further computation. Is there something? Oh yeah, the one other thing I wanted to show you is there's a little flavor of non-monotonicity in this if you compare 6D and 6F. Because 6D said if it didn't land on 1, it landed on 2. But then once you update on it landed odd, suddenly you reject that conditional and replace it with if it didn't land on 1, it landed on 3. And that shows you that there's a variably strict feel for this for those who are interested. Okay, so anyways, that's our semantics for the language. Is every sentence is a set of paths. So then if we want to assign probability conditionals, what we need to do is generate a framework for assigning probabilities systematically to sets of paths. Because then what we're going to say throughout is, well, the probability of a sentence is the probability of the set of paths at which it's true. So now we need to tell you how to assign probability to sets of paths. And that's section 3. And the way this is going to work is what we do is we go in 2 steps. First, we assign probabilities to worlds. And then we use our probabilities that we assign to worlds to construct a probability assignment to paths. So we're going to be able to tell you the probability of each path based on the underlying probability function over worlds. And then the probability of a set of paths is the sum of the probabilities of the paths in it. And the probability of a sentence is the sum of the probability of all the paths at which it's true. But the key thing is what's philosophically primitive here is your probability function over worlds, which might be measured by your betting behavior and descriptive claims. And then we use that to construct a unique probability function over paths. So we have probabilities over paths, but they supervene on your probability measure over worlds. And we'll show you how all that works now. So to do that, we introduced 2 definitions. We got the proto-epistemic space is the probability measure over worlds, and then the epistemic space is the probability measure over paths. So the proto-epistemic space is we suppress this I think sample space, the algebra, because we assume whenever you have a set of thingies, you're going to assign probabilities to the power set of it. So the proto-epistemic space is a pair of a set of worlds and a probability measure over the power over every subset of that set of worlds. Okay? And that's the familiar thing, is probabilities over worlds. And now the unfamiliar thing is the epistemic space, is we have a set of paths, and then we assign a probability to every subset, every possible set of paths that's a subset of P. So that's our notation. And then the key is we introduce a procedure for if you have a probability measure over worlds, a proto-epistemic space, you induce a unique probability measure over paths. And so we're thinking of the agent as having a unique probability measure over worlds, and it induces a unique probability measure over paths, so that when we talk about probabilities over paths, it's really just a very long-winded, abbreviated way of ultimately talking about their credences in worlds. Here's how it works. And this is the key thing. And also this is inspired by a related thing that Justin Koo has been working on, is this way of constructing things, but there's you have to do a lot of squinting, but it's there. Okay. So this is what we say now. Okay, you have your probability measure over worlds. You have a set of worlds and a probability measure over it. And now we want to create an epistemic space with the paths. And so here's how we do it. First of all, you have P, which is your set of paths. And the set of paths is the set of all paths that you can create from the worlds in W. So you have to take all of the worlds in W, and to make a path, you have to take each of them. You can't skip any. You take each one, and you put them in order with no replacements. And every way of doing that, that's P. And now the key is that we define C in terms of PR. So we define the probability measure over paths in terms of the probability measure over worlds. And here's how we do that. The probability measure of any set of paths is the sum of the probability of the individual paths. And the key is that the probability of an individual path is defined in terms of the probability of worlds. And here's how. Suppose you have a path W1 to Wn. What you do is you take a product of a bunch of terms. You take the probability of W1, and then you multiply that by the probability of W2 divided by the probability of not W1. In other words, the conditional probability, I should have written conditional probabilities. So it's W1 times the probability of W2 given that you're not in W1 times the probability of W3 given that you're not in W1 or W2, and on until the probability of Wn given that you're not at any of the worlds in W1 through Wn minus 1. So metaphorically, it's like you take each world and you take its probability conditional on that you're not at any of the earlier worlds. And so in a way, it's like probabilistically, the earlier you are in the sequence, the more probability mass you get, the more weight you get assigned, because you're more likely. And to get to the next world, the previous ones have to all be ruled out. And so when you're thinking about the probability of the next world, you say, well, given that we've ruled out all the other ones. But that's really just a metaphor. I don't really know what it means, but the equation is what matters. Okay. And then we say, well, an epistemic space is well behaved means that there exists a probability measure over worlds that induces that epistemic space. And the key is some epistemic spaces can be constructed in this way and some can't. And you're rational only if you did construct it this way. So it's a constraint on rationality that the agent's epistemic space be well behaved. So now let's do an example. Okay. So in this example, and this is a different example than before. You can think of this example as like the same model with a die that has 3 outcomes, but imagine that we've learned something. We got some testimony about how the die landed. So we've eliminated that the die landed 4 through 6, and also it's more likely that it landed 1, and then more likely that it landed 2, and then least likely that it landed 3. For some reason, someone told you all this about the die. Okay, so this is the model. It's a 3-world model now, 1, 2, 3, and your probability measure over worlds weights them, half, third, a sixth. And that's reflected in the table on the left. And then the table on the left induces the table on the right via this lift thing. And that's what I want to walk through to give you a feeling for how this works. The key is that the probabilities on the left determine a unique probability function on the right table. And I'll walk through how that works with one example. So each of these paths, the probability of each path is computed from the left. And here's how. Let's just do the first path. The first path is 1, 2, 3. So at that path, for example, it's true that the die landed 1, and it's also true that if it didn't land 1, it landed 2, and it's also true that if it didn't land 1 or 2, it landed 3. You can feel the fallback nature of the further worlds in the path. How do we compute its probability? Well, what we do is we take the probability of world 1 and do that times the probability of world 2 divided by, given that we're not in world 1, times the probability of world 3, given that we're not in world 1 or world 2. First thing I want to observe in this is that whenever you compute path probability, the last world falls away because it's the probability of that world divided by itself. So you never worry about that. Okay. And then, so really what this comes down to is the probability of world 1 times the probability of world 2 divided by the probability that you're not in world 1. And when you compute that, you get, well, it's 1/2 times 1/3 divided by 1/2, which I'm told is 1/3. Okay, so that's how these get computed. So you get the feeling of it in general. You got the probabilities over worlds, and then you use them to get the probabilities of the paths. Okay. Before we go to the next thing, I just want to show you, so like you have this table with all the paths, and I just want to think through what kinds of claims are true at which path. So we've got 6 paths there. Now notice that for descriptive claims, a descriptive claim is true at the path just in case it's true at the first world of the path. Yeah? And so that means that the die lands 1 at the first 2 paths. It lands 2 at the second 2 paths, and it lands 3 at the last 2 paths. So what's the probability that the die landed 1? It's the probability of the first path plus the probability of the second path. And by the way, when I say what's the probability, I mean using the path function, because the path function is what assigns probabilities to the sentences of our language and to conditional. So that's what we really care about in terms of getting predictions about the probability of sentences. So the probability that the die landed 1 is the probability of the first path plus the probability of the second path. And what's cool is that's 1/2, which is what the original probability function over worlds assigned for the die landing 1. Oh, there are questions here. Oh, I'm so sorry. Oh, I don't know the answers to those questions, though. We've wondered this before. It's good to think about. Yeah. Good questions. Yeah. I would say probably and maybe. Okay. So, but the key is, that's what's really cool, is this way of building probabilities of paths from probabilities over worlds guarantees, it always preserves the probabilities of non-conditional sentences. Okay. And then the reason that we use this construction is that you can prove, which I'm not going to prove, but I'm going to illustrate with an example, that whenever A and B are descriptive and your epistemic space is well behaved, you satisfy Stallneckers thesis. So the probability you assign to if A then B, to the set of paths where if A then B is true, is equal to the conditional probability of B given A. Okay, so I'm not going to prove that for you today, but I'm going to prove that it holds in one example. Okay, so I'm going to give you a feeling for why it holds. And the example we'll do is the conditional, if the die landed 1 or 2, then it landed 1. So if we're in world 1 or world 2, then we're on world 1. So if it didn't land 3, it landed 1. And so the way we're going to compute this is, first we're going to find the set of paths where the conditional is true and calculate its probability by summing each of the paths where it's true. And then we're going to calculate the conditional probability of the consequent given the antecedent by finding the set of paths where the consequent is true and the set of paths where the antecedent is true, and I'll show you they're the same. So first of all, the conditional, if the die didn't land, if the die landed 1 or 2, it landed 1. What paths is that true at? If we're at world 1 or world 2, then we're at world 1. Well, paths are linear orderings. And this conditional is true at a path just in case world 1 is before world 2 in the path. Because the idea is, well, to evaluate this conditional, you zoom in to just the worlds in the path where 1 or 2 is true. You make the subpath where just those are true. And then it's got to be that the first world in that is a path where 1 is true. So it's got to be that world 1 is the first world when you zoom in. So let's look at our 6 paths. So take the first path, 1, 2, 3. If you zoom into 1 or 2, you remove 3 from the end. So you just have the 2 world path, and 1 is before 2, so 1 is the first world in that path. And so since 1 is the first world in that path, the consequent is true there. Let's look at the second path, 1, 3, 2. You remove 3, you get 1, 2. Notice you get the same path. When you update each of those paths, when you update each of them, you get the same thing out. 1, 2, and 1 is before 2, so it's true there. But now look at the third path. Third path is 2, 1, 3. When you remove 3, you get the subpath 2, 1. 2 is before 1, so that means, well, 2 is at the first world. That means that at this subpath, the die landed 2. It didn't land 1, so the conditional is false there. Summarizing 8b, this conditional is true at the 3 paths where 1 is before 2. That means the probability of the conditional is the sum of the probability of the first path, the probability of the second path, and the probability of the third path. So it's 2, 6, 1, 6, 3 30ths, which I'm told is 3 5ths. Okay, so that's the conditional probability. And now, that's the probability of the conditional. And now let's do the conditional probability. So now we've got to do, okay, how likely is the so we have to find the set of worlds where W1 holds and divide that by the set of worlds where W1 or W2 holds. Or not worlds, the set of paths. So what are the set of paths where W1 holds? That's the set of paths where W1 is the first world in the path. And that would be the first 2 paths. And then what about the set of paths where W1 or W2 is true? That's the set of paths where 1 or 2 is the first world, which would be the first 4 paths. So this is the probability of the first 2 paths divided by the probability of the first 4 paths, which is 2, 6 plus 1, 6 divided by 2, 6 plus 1, 6 plus 3 12ths plus 1 12th, which I'm told is 3 5ths. Okay. I don't know if that was really illuminating, but it was illustrative. Okay. So anyways, look at that. 3 5ths is equal to 3 5ths. And that is our illustration of why Stallneckers thesis holds in this system. I will have I'll do a second illustration later that uses a picture. Maybe that'll be more illuminating. I don't know. Okay. So now here's where we are so far. I've given you a theory, and I've shown you that it validates Stallneckers thesis. But we started this paper by showing that Stallneckers thesis leads to triviality, leads to any two claims being probabilistically independent. But also you can see that in our theory, there are probabilistic dependencies between claims because, I mean, just look at it. We have this little table that gives you the probabilities, and they're all, clearly you're going to get some dependencies here. So something must have gone wrong. And what went wrong is that we have rejected closure. We reject conditionalization. Here's what that means is, for us, what we've shown is if you have a well-behaved epistemic space, you validate Stalnaker's thesis. But what's going to happen is if you take your well-behaved epistemic space and you conditionalize it on a new claim, you're no longer well-behaved and you no longer validate Stalnaker's thesis. And that brings us to the final substantive section of the talk, which is where we give our theory of how to update your beliefs with new information and your conditional beliefs. And it's not conditionalization. It's something we call hyperconditionalization. It agrees with conditionalization about your posterior probabilities assigned to any claim that's not a conditional, but it has a different prediction about your posterior probabilities assigned to conditionals. And so for whatever reason, we call it the hyperconditionalization. So the first thing I want to show you is why you can start with a credence function over paths that satisfies Stalnaker's thesis, conditionalize in the ordinary way, and no longer validate Stalnaker's thesis. So that's the first thing I want to show you. So first of all, we define conditionalization, which I probably should have done earlier. Can you conditionalize on an epistemic space? That's definition 7. That just means that, well, once you've updated on A, your posterior that you assign to B is equal to the ratio of your prior on B and A divided by your prior on A. So what I want to show you now, what this table is I took the previous table, the previous credence measure over paths, and I conditionalized it on A. Or no, not on A. What's A? On not W1. So the die rolled 1 or 2. No, the die rolled 2 or 3. The die rolled 2 or 3. That's what we're conditionalizing on. So how do you do that? Well, the way you conditionalize one of these tables is you delete the rows where the claim you're conditionalizing on is false, and then you renormalize by preserving all of the remaining ratios, but but making them all equal to 1 or whatever. You know what I mean? Maybe. Okay. Do I know what I mean? Okay. So anyways, that's what you get here. This is the result of conditionalizing. So we want to say we're conditionalizing on it landed 2 or 3. That's false at the first 2 paths in the previous table. It's false there. So they are eliminated. And then the remaining paths, whose ratios are not perspicuous. The remaining paths, it turns out, had these ratios to each other: 1/2, 1/6, 1/5, and 2/15. And so that's what you, oh, I see. Here's how you see it. Well, you've removed 50% of the probability mass. So you have to take all of these probabilities now and divide them by half, or divide them by half? Yeah, divide them by half. So multiply them by 2. So you had 1/4 for the third path, and now it's 1/2. So that's conditionalizing. And here's what I want to show you, is that I want to show you 2 things. First thing I want to show you is that in terms of our probabilistic models, this posterior credence function is not well behaved. And second, I want to show you that it doesn't validate Stalnaker's thesis. First of all, here's why it's not well behaved. It's difficult to be well behaved because when you're well behaved, your credence in different paths have to respect each other. They have to cohere in a certain way because they're defined in terms of the underlying probabilities of the worlds in the paths. And here's the illustration. In this posterior distribution, the probability you assign to W1 to 1, 2, 3 is 0. But now go back to definition 5, where we said what it took to be well behaved. What do you have to satisfy? Well, in order for 1, 2, 3 to be 0, the product on the right-hand side of definition 5.2 has to be 0. So that means when you multiply the probability of W1 times the probability of W2 given not W1 and so on, it has to be 0. But you're multiplying all these things. So if multiplying all these things takes you to 0, one of the terms in them has to be 0. But if one of the terms in them has to be 0, then that means either W1 has a probability of 0 in the underlying measure over worlds, or one of these conditional probabilities is 0. But if that was the case, all of the paths would have a probability of 0. Because, yeah, something like that. Okay. So anyways, that's what shows you that that this posterior is not well behaved. There does not exist a probability measure over worlds where if you try to compute the probability of each path using that probability measure over worlds, you could get this posterior, because some of these paths have probability of 0, even though the underlying measure would have to assign a positive probability to all the worlds of them, since some of the other paths have a positive probability. That's the basic thing. And now what I want to show you last is that when you take our nice well-behaved distribution and conditionalize it, you get violations of Stallneckers thesis. So here's the example. The violation is in 9b and 9c. So we have a conditional probability that's 1 and a probability of a conditional that's less than 1. So conditional probability of 2 or 3 given 1 or 3 is 1. Why is that? Well, that says what's the probability you're at a path whose first world is 2 or 3, given that you're at a path whose first world is 1 or 3. Well, if you look, the only paths that get any probability have a first world being 2 or 3. So the probability that you're at 2 or 3 is 1. After all, that's what you conditionalized on. So even when you conditionalize on being in 1 or 3, it's still 1. And you can just see that. You see, well, the paths were 2 or 3, that's the last 4 paths, and they add up to 1. And when you zoom in to 1 or 3, it doesn't change. Okay, so that's 1. But now think about, this is the crucial thing. The crucial thing is 9c, is the probability of the corresponding conditional is less than 1. What's the probability that if you're at 1 or 3, then you're at 2 or 3? This is the key. Why is that? Well, what we do is we're asking what paths is this true? And the problem is it's false at some of these paths. And the reason it's false at some of these paths is that when we conditionalized all these paths, even though we were like trying to remove W1, we were conditionalizing on not W1, these paths that remain still have W1 in them. It's just not at the first world. But remember, paths that are later, worlds that are later in the path can still affect the truth value of conditionals. And so the problem is this W1 hasn't been removed. And so, for example, so we want a path where this conditional is false. So let's find one. I think it's the 6th path. No. Or is it I think it's the 5th path. So the 5th path is where it's false. Because take the 5th path and update it with the antecedent 1 or 3. Oh no, that's not the one. Which one? Paolo, help me. Oh, I think it's the 3rd path. It's the 3rd path. Paolo, you're muted. And I figured it out. Okay, it's the 3rd path. Okay, so the 3rd path, imagine updating the 3rd path with either 1 or 3. 3rd path starts with 2, so you remove 2. And now you have the path 1, 3. And the consequent 2 or 3 is false there, because at the first world in this updated path, 1 is true, not 2 or 3. And so the problem is, so the conditional is false there, and that has 50% of the probability measure. So actually, the probability of this conditional is 1/2. Okay. What went wrong here? The thing that went wrong is that we're trying to learn that W1 is gone, that we don't have W1. But even once we've learned this by conditionalization, you could still have agents who have conditional belief that W1, which means they can still assign positive credence to conditionals with W1 and the consequent. And that corresponds semantically to saying, well, you conditionalize on not W1, but you still are assigned positive mass to paths that have W1 in them later, which means at those paths there can be conditionals that are true that remove some other things and then have W1. So that's the problem. Enter hyperconditionalization. So what we say is no, when you update, you don't conditionalize, you hyperconditionalize. And what that means is you have to take each of your paths that you originally assigned probability to, and you have to look at each of those paths and you have to remove W1 from that path. So it's not, so the key is that when you're done learning, you're gonna assign probability to a completely different set of paths than you did initially. It's not that you have all the paths and then you learn A and now you assign probability to a subset. But you take each of the paths and then you make each of the paths learn A, And now you have a new path that has learned A, and now you assign probability to the new paths. So here's how we do that. What you do is, if you want to learn A, you go pointwise, path by path, and you update each of those paths with A using the path update operation, which means you go into that path and you remove every single not A world, and then you just preserve the order of what remains. And now you assign probability to all these new paths, subject to the requirement in 8.2 that oh, I see. Okay, and then here's what you do. Now you need to calculate a new probability measure over the new paths. And here's how you do it. Each new path was derived from an old path. And the probability of the new path is the sum of the prior probabilities of the old paths that you derived it from. So that corresponds to something called imaging in ordinary probability stuff. It doesn't really matter for this. Okay, and let me show you that before I go on to, oh, and then, sorry, and then just the probability of a set of paths is just the sum of the probability of the individual path. So the key is 8.2, which tells you how to compute the posterior probability of an individual path, which is again by summing, I'll only just unpack that, it's the sum of the prior of any path P prime, such that the new path P is found by taking the old path P prime and updating it with A. So let me illustrate that with an example. Suppose you want to learn that the die landed on 2 or 3. You have your 6 paths that are 3-world paths. The first thing you do is you update every single one of those paths with the claim that the die landed on 2 or 3. And that's in 10b. And you can see that when you do that, you're going to get 2 different kinds of paths out of it. Either 2 is before 3 or 3 is before 2. So if you update 1, 2, 3 with not 1, you get 2, 3. But if you update 1, 3, 2 with not 1, you get 3, 2. So we started with 6 paths. We end with 2 paths. So each of the posterior 2 paths came from 3 paths originally. We got these 2 paths, 2, 3, and 3, 2. Notice neither of them has world 1 in it. And that's how we're responding to that earlier issue. World 1 is gone. The probability of 2, 3 is the posterior of 2, 3 is the prior of 1, 2, 3 plus the prior of 2, 1, 3 plus the prior of 2, 3, 1. And likewise for the probability of 3, 2. Okay, so that's an example of how all this works. Before I get to the rest of the substantive material, I want to illustrate the example with some enormous figures that are at the end of the handout. So we're going to go to page 4 now, and I'm going to go through everything I've said so far, but now with these enormous figures to illustrate in a different way. So there's no new material now, it's just a different example, think about a different way. And then at the end, I'm going to go back and close with kind of the signature properties of the account we've developed. Okay, so now we got a new example. We got a 4, I'm sorry, they're all different examples, you know. You have a 4-world example. So 1, 2, 3, 4. Again, you can think of this as like the 4 die. Imagine you rolled the die, and then you got this, you know, God told you that you've eliminated 5 and 6. So that's where we're at, but you're indifferent over 1 through 4. So that's the situation we're modeling. And what we have in these images is we have the set, we're representing diagrammatically the set of all paths. And we've partitioned the set of all paths into cells. And each of the smallest cells is an individual path, but you can see how they're divided up into different chunks. And it's helpful to divide them up this way. It's good to think about. So the columns, the columns of this are the coarsest way of dividing them up, which just says, what's the first world of each path? So the first column is the set of all paths whose first world is 1. In other words, the set of paths where it's true that the die landed 1. So you got 1, 2, 3, 4, 1, 2, 4, 3, 1, 3, 2, 4, 1, 3, 4, 2, and so on. And then you see how the rest of the diagram works. And in this example, we're measuring probability by the proportion of the region that it takes up. And you can see the agent is indifferent over each path and over each world. And you can see that because they assign equal probability to each of the cells. Okay. Now, figure 2. So that's the illustration of just what paths are and how to assign probability a little. Figure 2 is the illustration of when is a conditional true at a path and what's the probability of the condition. So let's think about the conditional if 1 or 2, then 2 or 3. So if the die landed 1 or 2, then it landed 2 or 3. In other words, if it landed 1 or 2, it landed 2. So that conditional is true to path just in case if you take the path and you zoom into the worlds in the path where 1 or 2 is true, 2 is the first world. So that means 2 has to precede 1. And we put in gray the paths where that holds. So for example, 1, 2, 3, 4 is not in gray because the conditional is false there, because when you update it with the antecedent, you get the path 1, 2, and 2 or 3 is false there because it's false at the first world in the path 1, 2. Okay, so do you see that like the smallest divisible unit in these diagrams is like the thingies, you know, they're kind of like very long little chunks, and it's just like the cell that has 2, 1, 3, 4, for example. You can count the probability of the conditional by going, there's a total of 24 cells, as you can count, and they're all equally probable. So you can count the probability of the conditional by counting how many cells. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the probability of the conditional is 1/2. And think about what's the conditional probability of 2 or 3 given 1 or 2? It's the same as the conditional probability of 2 given 1 or 2. So it's 1/2 because this agent's indifferent about how the die landed. So if it landed 1 or 2, what's, you know, conditional on landing 1 or 2, the credence that it landed 2 is 1/2. So you can see here, this is another example where Stallneckers thesis holds because the probability of the conditional is 1/2, and that's the conditional probability. Okay, figure 3 shows you why conditionalization is wrong. If you want to conditionalize on not W1, what you would do is just remove, again, we didn't even space this right. You remove the leftmost column. So we've removed the W1 column. That's what conditionalizing is. And then you renormalize. So now the probability of the conditional is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, but now divided by 18. So it's 2/3. Whereas the probability of 2 given 1 or 2 is still 1/2, I think. Wait, is it? No, it's 1. Sorry. The probability of 2 given 1 or 2 is now 1 because we've ruled out 1. So it's the same as the probability of 2 given 2. And you can see that by saying, look, 2 is true at every world where 1 or 2 is true. At every path where 1 or 2 is true, 2 is true. And then the last page has hyperconditionalization. This is a good one. Okay, so hyperconditionalization, this figure has 2 halves, the top and the bottom. The top is we took our earlier diagrams and we just split them up so that we could put arrows for readability. So that's the top half is the same diagram as in figure 1, except we've dotted, you know, 2 of them, you know? You see that? So it's like the top half is the leftmost 2 columns of figure 1. And if you want to hyperconditionalize on not W1, what you do is, and it's a ... So you'd actually do it for all 4 columns, but we just didn't, you can't visually process it with that many arrows. So we just illustrate what it looks like for the first 2 columns. You go to each path and you move its probability, which is what the arrow shows, to the result of updating that path with not W1. So I'll give you an example. Look at the very top left path in figure 4. So that's 1, 2, 3, 4. If you update it with not W1, then you would get the path 2, 3, 4. So if you want to do that hyperconditionalization, you take its probability and move it with the arrow. Well, that's a very difficult arrow to follow. Okay, different one. Look at path 1, 4, 2, 3. Okay, that's the bottom left of the top. So 1, 4, 2, 3. If you update that with not W1, you get the path 4, 2, 3. And so its probability moves to the path 4, 2, 3. And again, the gray, so the bottom thing is the posterior distribution, which again, you can see the posterior distribution is all assigned to a different set of paths than the prior. So it's not like in regular conditionalizing with possible worlds where you have a set and you conditionalize, you zoom into the subset. It's not like that. You know, it's a non-eliminative update where you move to a whole new set of paths. And what else? And then the gray is where the conditional is true. So you can see the conditional has a probability of 1 after updating, which is what we want. Anyways, okay, so that's our second illustration. Now we return to page 3 and do theorem 2 and theorem 3, and that will be the end. We're not going to do 11 and 12. I don't know what they mean anyways. Okay, so theorem 2, what does that say? Oh yeah, so this is like the really, why hyperconditionalization? Why hyperconditionalization? Here's why. is hyperconditionalization is it's like a supervenient update. Because here's what you're like in life is you have your credence measure over worlds, and that's what's fundamental about you. And that credence measure in worlds induced a credence measure over paths. When you want to learn that it's raining, you want to learn a new thing, really, what's fundamental about you is your credences in worlds. And when you learn the new thing, what you really want to do is update your credences in worlds. And then you get the new paths. Like at the end of the day, what you're really doing is updating your credences over worlds. And here's what the formal thing is that corresponds to this, is it turns out that if you hyperconditionalize on a descriptive claim, like it's raining, that's equivalent to taking so imagine you're represented not just with your credence measure over paths, but also with the credence measure over worlds that induced the path measure. If you want to update your path measure on the claim that it's raining, take your world measure, conditionalize it on it raining, and then use the new conditional measure to induce a new probability measure over paths. And if you do that, that's what hyperconditionalization says happens to your path measure. So basically, an agent who is hyperconditionalizing their path measure is the same as an agent who's conditionalizing their underlying world measure and just re-lifting after that to get a new path measure. And that, which I'm not going to prove for you, but what I will prove for you is if that's true, then theorem 3 is true, which is what matters empirically. Because theorem 3 says that the class of well-behaved epistemic spaces is closed under hyperconditionalization. So if you have a well-behaved space and then you hyperconditionalize, you get a new well-behaved space. That was what failed for conditionalization. We had a well-behaved space. Well-behaved means that the measure over paths is derivable from a measure over worlds. And we saw with conditionalization, you can have that and then conditionalize and then not have it. And having that is what you need for Stallneckers thesis. So that's why Stallneckers thesis failed after you conditionalize. But theorem 3 says that hyperconditionalizing never takes you from a measure that validates Stalnaker's thesis to a measure that invalidates Stalnaker's thesis. And that's what we want. Because we want to say that really rational agents always satisfy Stalnaker's thesis. And they also can learn things. And the idea is you start by satisfying Stalnaker's thesis, then you learn a new thing by hyperconditionalizing, and then you still satisfy Stalnaker's thesis because you're still well behaved. And the reason I can prove for you theorem 3 holds, because theorem 2 is a constructive proof of theorem 3, because theorem 2 says that if you start out well-behaved and you have a credence measure over worlds that gave you your credence measure over paths, and then you hyperconditionalize your measure over paths, that just means that you took your measure over worlds and conditionalized the measure on worlds and then constructed a new path measure. So in particular, the reason that E plus A, hyperconditionalizing on A, is well-behaved, the reason that E plus A is guaranteed to be constructed from a measure over worlds is that it's constructed from a particular measure over worlds, namely the result of taking the original measure over worlds and conditionalizing it on A. Okay, that's the end.